back to Corona Chemistry, where we're going to dive into Unit 2. As always, you can find links to the notes and the slides that we are going to be utilizing in our discussion today down below the video. So feel free to click on those Google Drive links and access the completely public files to follow along. Or just kick back, relax, and plant those eyeballs firmly on the screen, not directly, okay? But here we go! Diving into Unit 2, which is, in my opinion, not nearly as much of a snooze fest as Unit 1. Unit 1, oh my goodness, horrifically boring. Necessary, but horrifically boring. Unit 2, a lot of terminology, not a lot of math, but super, super necessary and imperative for the future discussions that we're going to have. I would say chemistry begins next unit, okay? But we got to have a more broad background as well. Unit 1 is not enough. So here we go. Unit 2, matter and change. Let's start off with a few definitions here. Matter is, of course, what chemistry is studying, the study of matter and the changes that it undergoes. Well, what is matter? Remember that it's anything with mass and volume. And if you'll recall, there's not too many things in the universe that don't fit that description. There's only a few exceptions. Light, energy, those are the main exceptions to stuff that isn't matter. Pretty much everything else is. Well, what is this matter comprised of? The matter is comprised of various combinations of atoms. Atoms are the smallest units of elements that make up absolutely everything around us. Everything that you can reach out, touch, grab, and feel is made of some combination of these atoms. Well, what are these atoms? It could be one of 118 different elements on the periodic table. This entire universe that we know is comprised of 118 different elements. Currently, there could be more, right? Theoretically, there's an infinite number of elements. We just haven't gotten there yet. But as of right now, our known universe is comprised of 118 elements. Insanity! And a compound, and I know you've heard that word before, and it can be used in a variety of ways. In chemistry specifically, it is a substance that is made of two or more types of atoms. And they're not just holding hands. Think of them as welded together. Okay, they are chemically bonded. Now, we don't really know what that means just yet. We're going to talk about that a whole lot further on in this course. It's a very, very important concept, but they are welded together. So it doesn't matter how strong you are. I've got 22-inch circumference biceps, and I reach in, I yank on these two atoms as hard as I can, and I cannot pull them apart because they are chemically bonded. The only way to break a chemical bond is through chemical means. No matter how strong you are, you're not going to be able to accomplish that. A molecule is a slightly different definition. As far as we're concerned right now, it's essentially another word for a compound. Specifically what it is, though, is it is a compound that is utilizing a specific type of bond known as a covalent bond. But we will talk about that a little later on in the course. So for now, let's look at how these compounds are written. I'm sure we've seen chemical formulas before. Maybe we haven't written them ourselves, but they're pretty easy to get the hang of. So why not introduce them now? And NaCl is one of the most common ones. It was quite possibly the first one you ever saw. That or H2O. We've got two of the most common formulas right here on your screen in front of you. And how is it written? Well, it's just like in math. If I don't see any numbers, then it's an understood coefficient of 1, right? And so NaCl is 1 sodium. Na is sodium on the periodic table, and 1 chlorine. Cl is chlorine on the periodic table. So it has one of each, and they are chemically bonded together. They are welded together, and they're not coming apart unless some chemical comes along to give them a good reason to split apart. Okay? So 1 and 1. Well, what else can we incorporate into these formulas? We can incorporate what are called subscripts. And subscripts, the number that is written below, of course, only applies to the number that it is directly adjacent to. So in the instance of H2O, it's 2 hydrogens and 1 oxygen. That 2 does not apply to the oxygen. And because there's no number explicitly written there, there's only 1 oxygen. We can also incorporate parentheses. And parentheses work just like they do in math. It only applies to what it's directly outside of. So right here we have a calcium phosphate, Ca3PO42. This 3, the subscript, is only going to apply to the calcium. This 4 is only going to apply to the oxygen. However, this 2 on the outside is going to apply to both the phosphorus and the oxygen inside of the parentheses. I know you're going to get used to all the elements on the periodic table. If you haven't already studied most of the elements, you definitely should be looking at it, okay? Because quite often we're going to be just using the name of the elements instead of just saying the symbols, so you want to get used to them. You got to know what them. You can't get out of chemistry without knowing what the elements are. But we can also use coefficients, and these coefficients work just like they do in math as well. the distributive property is what I always think of. So this 6 on the far outside gets carried all the way through the K3P, the potassium phosphide. So 6 times 3 is 18 potassiums, and 6 times 1 is 6 phosphoruses. Excuse me. So you can utilize those same strategies when you're calculating how many of each element are present right here. 12Al2SO43, that's aluminum sulfate, or 42SR3PO32, strontium phosphite is what those are. So feel free to incorporate those same strategies. One of the main topics of today are the different states of matter. And this is something that you're like, why the heck are we wasting time on this? I know the difference between solid, liquid, and gas. I learned it in second grade. I learned the differences. Yes, you probably did. But what we're going to do is we're probably going to take it one step further than what you have before. We're going to describe the differences on a molecular or an atomic level. And that's something that, if this really is your first rodeo in chemistry, I can pretty much safely say that you cannot do. So, yes, there are 4 states of matter: solid, liquid, gas, and plasma. Plasma is only going to take up a small portion of this conversation. He's not going to be really included in any of our assessments or anything like that, but we will talk about him. But mainly solid, liquid, and gas, because that's what we're going to be working with in labs and in all the chemicals that we're talking about. So let's begin. Walk with me on a journey through solid, liquid, and gas, where we're going to be looking at the same flask of water for solid, liquid, and gas. And this water is going to go through some changes, just like all of us. Okay? Just like all of us. So we start with a zoomed in picture on these ice cubes, and you can see all these molecules densely packed together, little pockets of air in between all the molecules, but definitely stuck in their place. Okay? H2O. We're going to be using this similar terminology for solids, liquids, and gases. Solid has a definite volume and a definite shape. Just think about it. You're sitting at a desk in school, or maybe you're sitting at a desk at home, or on your couch at home, or you've got your smartphone in your hand. No matter how I bend this, shape it, unless I'm literally breaking it or cutting it in half or anything like that, it's going to maintain its same shape. Therefore, it's going to maintain the same amount of space that it occupies, aka the volume. So solids are not changing their ways in that regard. And the atoms are packed together in fixed positions. However, a common misconception is that the atoms or the molecules that make up the solids aren't moving at all. That's not true. The solids are vibrating constantly in place. Now, you can't see that with your naked eye, but they are constantly moving. There is some amount of kinetic energy within these atoms or these molecules that we are looking at. It's just very, very small. So, of course, we cannot see it. But one of the new terms that we're looking at is that they are very attracted to each other. They're unable to suppress their feelings. They want to be there, right? Just think about it. Why does the phone stay the way? Why doesn't it melt away into hundreds of millions of different pieces? Well, it's because the atoms like each other. They like each other a whole lot. They're attracted to each other. Hot chemistry for each other. And another term for that is strong intermolecular forces. But it is simply saying that these atoms want to be with each other. They are attracted to one another. They can't ignore their feelings, which can be a blessing and a curse. Am I right, ladies and gentlemen? Am I right? Let's go on a journey. Moving on to liquid. Whereas solid was definite volume and definite shape, liquids indefinite shape, definite volume. Think about it. You've heated up one of those wonderfully convenient Campbell's tomato soups to go. You know, in those like thermos cups that you can sip on soup, but sipping on soup feels so unnatural. And so let's say the soup is 250 milliliters, and you go, my goodness, soup is meant to be enjoyed via spoon. You're not supposed to drink soup. You eat soup, you fool. And so you take your soup in its thermos shape and you pour it into a beautifully done just ivory soup bowl. And of course, it's 250 milliliters. It's going to stay 250 milliliters. However, it goes from thermos shaped to soup bowl shaped that you're eating in the very elegant dish that you selected. So it changes its shape, but it's not going to change the volume that it's taking up. And these molecules are in constant motion. They're not as attracted to each other as the solids. They still want to be with each other. They still absolutely want to be with each other. However, we can learn a little from this, ladies and gentlemen, especially those of us stuck in high school still. They can overcome their feelings. They can suppress their feelings. They're working on themselves, ladies and gentlemen. They're working on themselves. Johnny, listen, I know you feel it too. There's something between you and me. And if it's meant to be, then it's going to be meant to be, a couple years down the line. But let's take this time to work on ourselves. Because how can we be the best we can be if I'm not the best me can be, do you feel? Call me in 2 years, Johnny. Okay? I'm working on me. I'm studying chemistry. Okay? I'm going to get an A. You're so handsome, though. Stay you. But, improve. Work on yourself. And that's what the liquids are saying to each other. They're attracted to each other, but they're able to flow over one another. That's why you're able to take this pitcher of Country Time lemonade and pour it into the glass. The molecules like each other a whole lot, but they're able to suppress their feelings in order to slide past one another. So the atoms are close together. Typically, it's a little more space apart, the molecules, when comparing solid to liquid. However, water is one of those exceptions, and we'll talk about that a little bit later on down the line as well. But that has to do with the fact that when water freezes, it actually traps air pockets in between those molecules, which is something that doesn't occur in absolutely every substance. So liquids typically have a little more room to breathe when compared to solids. It's just that water is one of those exceptions. But either way, they're kind of stuck in the middle in terms of their kinetic energy. They're moving a little bit more than solids, but of course less than gases, as we're going to come to talk about. But definitely hold on to these indefinites and definites as we're talking about our solids, liquids, and gases. So we're looking at that same flask, right? It looks a whole lot different. Come with me to the final stage. They're all grown up. The sun has been beating down on this flask, and the water has absolutely evaporated, becoming a gas. Water vapor. So, gas has an indefinite shape and an indefinite volume. What gases do is they always fill their container. A lot of people have the misconception of, are they adding molecules? When you say fill their container, does that mean fill to the brim? No. It simply means that the molecules are getting as far apart from each other as possible. Imagine you're opening this flask of water vapor in the room that you're sitting in right now. One molecule is going to go off to the very far reaches of that corner. The other one's going to go off to the very far reaches of that corner. Right? They're going to get as far apart from each other as possible. In fact, the volume is whatever the volume of the room is. And of course, the shape is going to be the shape of whatever container you're putting it in. And if you're releasing it into the room that you're sitting in, the container is the room. So indefinite shape. Now, these guys are moving very, very, very fast. They've absorbed a lot of the heat, and that heat has been transferred to kinetic energy, which is why they have the highest kinetic energy. I can't move from solid to liquid unless I first absorbed enough kinetic energy to move from solid to liquid. And I certainly can't become a gas until I've absorbed enough kinetic energy as a liquid to convert to a gas. So, these guys are zooming. And because they're zooming so lightning fast, they barely have time to look each other up and down as they're passing by one another. So whereas there might be a teeny bit of attraction, it's fleeting, right? They're just zooming past one another, and they might give the old, but it's nothing long lasting. Okay, so there's definitely stuff there. It's just much weaker than the solids and liquids that we talked about so far. So we've gone a little bit deeper than what you've probably talked about before with these solids, liquids, and gases. Solids, strongest intermolecular forces, lowest kinetic energy, and they have a definite shape and definite volume. Those are the main things. You want to get comfortable with that terminology. You want to be able to describe things in that way. Liquids are right in the middle of everything. Liquids have intermediate intermolecular forces and intermediate kinetic energy, and they have an indefinite shape and a definite volume. Okay? And then gases, weakest intermolecular forces, highest kinetic energy, and indefinite shape, indefinite volume. So that is the gist of solid, liquids, and gases that we want to look at, and look at them all in the point of all in one view for us. We can see how the solids are arranged, the liquids are arranged, and how the gases are arranged. So let's talk about plasma. Plasma, there's not too many examples on planet Earth of plasma existing. It's a very high temperature state that cannot very readily be achieved here on planet Earth. And so the main example of plasma that we see on Earth, some might compare it to fire. Others say that the only example that we can see on planet Earth is lightning, actually, but it's a very high temperature state. And what's happening is the atoms are shedding their electrons through various reactions to the energy that is absorbed there. And so there's not too many examples here. The best example we can see, you just got to look up in the sky and look at the sun. Lots of plasma in there. And you might see in movies when people are saying plasma rifles and plasma lasers. Not necessarily the plasma that we're talking about here. And it's definitely not the plasma in your blood. A lot of kids will go, I learned about plasma. It's different plasma. Plasma, same word, different meaning. And the plasma in your blood is the liquid part of your blood. It is not this same high temperature state. You're not boiling on the inside, right? Right? I hope not. If you are, report yourself to a hospital immediately. But either way, it's not the same plasma, people, okay? And that's all we have to say about plasma. So bye-bye. Bye-bye. We won't see him again. Next, changes of state. We've talked about the difference between solid, liquids, and gases, but how do they get there? How do they get from solid to liquid to gas and vice versa? Well, look at this triangle. It has all of the phase changes, and you've probably heard of most of these. Solid to liquid. I throw the ice cube out on the sidewalk in the middle of the hot Texas summer, and what does it do? Sun beats down on it, it melts. Well, what do I do? I scrape up the remains, I put it into a cup, and I put it back into my freezer, and the freezer freezes it. Yes, of course, of course. And of course, you've learned about the water cycle. The sun's beating down on the lake, and what happens to the lake water? It evaporates. Another word for that, vaporization. Well, what happens when the water vapor goes up to the sky and becomes clouds? Well, that's condensation, right? But did you know that you could go from solid to gas or gas to solid, skipping the liquid phase entirely? That's crazy talk. That's absolute crazy talk. Well, the terms for that are known as sublimation when you're going from solid to gas or gas to solid. And if you're going from gas to solid, it's called deposition. Deposition. Kind of got a little lost in my train of thought here. And the reason why is because whenever I think of solid to gas and the fact that it's called sublimation, I always think of that song by the band Sublime, which no one knows. It's just full of scientists. I don't practice Santeria. I ain't got no crystal ball. But I had $1 million. Would I spend it all? If you don't know that song, please, it's Santeria by Sublime. Please add that to your playlist and culture yourself a little bit. I believe part of my responsibility here on this channel is to put a little bit of culture back into your generation, as your music tastes are just absolutely horrible. Okay, so I'm just trying to help you out a little bit, throw you a bone. So what are we going to do with these phase changes? Well, apart from having to know what the terms actually are, actually before we go on to that, let's talk about solid to gas, gas to solid again. There's very few examples of sublimation and deposition commonly known. And the best example of solid to gas, if you're in theater, you've probably seen this before. Or if you are a big aficionado with Halloween, you've probably seen this before. It's dry ice. Dry ice is literally frozen carbon dioxide, frozen CO2. And what it does, typically when you put it in water, is it immediately becomes fog. That's the fog that you're seeing on stage and around the spooky scenes in Halloween, typically. And so it immediately goes from solid to gas, skipping the liquid phase entirely. And there's not too many gas to solid examples at all, actually. In fact, the only real example I know of is sleet. When the water vapor goes up to the sky, freezes so quickly that it just falls instantaneously. And so sleet is that falling ice that we see. We see it quite commonly in Texas. We don't get too much snow. But sleet is falling ice from the sky, essentially. Or hail. That's what you can think of that as well. So where are we going to see this at? We're going to see this in the forms of phase change charts. And there's a couple different ways that we can see this. However, they all have the same structure. Okay? So this phase change chart consists of 3 sloped lines and 2 horizontal lines. That is the same for every single substance. Now, depending on the substance that you're looking at, it might be a steeper slope, a more shallow slope, might go a little bit longer than other slopes that you've seen in other. It depends on the substance, because we're working with the same axis on each of these phase change charts. The x-axis is you are adding energy into the substance. And the y-axis is, of course, as I'm adding energy, the temperature is going to go up. However, the temperature does not constantly go up. Notice here on these horizontal lines, I'm still adding energy, but the temperature's not going up. So let's talk about that. So with all of these structures being the same, the first sloped line is always going to be the solid. With the 3 states of matter that we are discussing, what state of matter exists when you're at the lowest temperature? Well, of course, that's solid. Therefore, the second slope line is always going to be the liquid. What state of matter exists when you're not too hot, not too cold? The liquid. And then, of course, what state of matter is at the upper reaches of the chart? That's going to be your gas state, which means that these horizontal lines represent the phase changes. Okay, very, very important here. And this is kind of a weird point that a lot of kids get confused on. The melting point is also the freezing point. We know water freezes at 32 degrees Fahrenheit, 0 degrees Celsius, right? That's when it gets that cold and it rains the night before. You're hoping for a snow day. But it also melts at 32 degrees Fahrenheit, 32 degrees Celsius. It just depends. Are we adding heat or are we removing heat energy from the substance that you're concerned with, that sort of thing? So, very, very odd there. Now, why is the temperature not going up? As I'm adding energy, where is it going? If the temperature is not going up and the kinetic energy is not increasing in my molecule, or sorry, if the temperature is not going up, where is that energy going? Well, the answer is the kinetic energy is changing in your molecules. That energy is being absorbed in order to convert your substance from one state of matter to the next. So if I am right here on this graph and I'm adding energy, what is happening is my molecules are being converted from solid to liquid. And remember what we said a few slides ago. You have to have a certain amount of kinetic energy to move from solid to liquid, because liquids, of course, have higher kinetic energy than solids. So without that kinetic energy, I can't phase change. So what is that energy being spent on? Well, it's being spent on the actual phase change itself. And let's say we're right here, we're a liquid, and we're becoming a solid. Well, what's happening? We're removing heat, but the temperature's not going down. It's because the kinetic energy is going down. The liquid molecules are losing kinetic energy so that they can then become solids. And of course, the exact same thing is going to happen on this horizontal line right here when you're going from liquid to gas or gas to liquid. The one weakness to this chart is it doesn't cover two of those phase changes that we talked about. It doesn't cover sublimation, solid to gas, and it doesn't cover deposition, gas to solid, which we will cover in example of a phase change chart that does. But for now, look at what you could see on a test or something like that. Same structure, the slopes are a little bit different. It doesn't even have, y-axis markings or anything like that. It just has letters, okay? And they could ask you a variety of questions. Where is the solid? Where is the gas? Where is this substance melting? Where is this substance boiling? And all you have to do is depict the correct letter. So make sure that you know the overall structure for this. You're not going to have to memorize any numbers or anything like that. They're always going to give you the graph. They might give you these letters that you have to associate it with. So now, let's look at another variant of a phase change diagram, which I like to call the butt diagram. As you can see, we've got cheek, cheek, crack. One giant butt, and every substance has a unique butt. Okay? Your left cheek might be a little bit bigger than your right. Your crack might be going a different direction. It all depends on the substance that you're looking at. But it always is structured the same way. Okay? It's always, when I'm at my lowest temperature, notice we've got temperature on the x-axis and pressure on the y-axis. That's a new feature. Solid is always going to be on the far left because that's when we're at the lowest temperature. Liquid is going to be the middle zone, and gas is going to be the far right zone. So the overall structure is always the same. It's just that you might have different size zones and you might have different direction of lines. Well, what these lines in between the different zones represent are the phase changes. As I go from this side to this side, I'm going from solid to liquid. What's that called? Oh yeah, melting. We've heard a lot of these phase change terms, and this is how we're going to have to apply it. So, let's look at a couple other terms associated with this graph. The triple point. Very, very, very cool feature, and I would encourage you to YouTube or Google videos on what a triple point actually looks like. It's difficult to achieve with a lot of substances, but a few of them are more readily achieved, such as cyclohexane. The triple point is where solid, liquid, and gas are all existing simultaneously. And that sounds like you might be questioning, what the heck does that even look like? That's why you got to go look at it. It's very, very, very cool. It's like they're all fighting to come to the forefront. And you can actually see all the examples. But where is that triple point located? It's where all three zones meet, of course. Where all three zones meet. And then we also have what is called the critical temperature. It's also known as the critical point. The temperature above which a substance cannot exist in the liquid state. So let's look at where that is on here. It's always going to be in the top corner of the graph that you're looking at. Why? Because no matter what I do to the pressure here, it's always going to be in this right zone, okay? Just imagine that this liquid zone stops right here. I wish this line went up a little bit further just to truly exemplify that. But either way, no matter what I do to the pressure, I can decrease the pressure, I can increase the pressure. The liquid zone is done. This substance has so much kinetic energy at this temperature that you cannot force it to be a liquid. Did you know that you can actually boil substances at room temperature? You can boil water at room temperature. If you decrease the pressure so much, if you decrease the pressure, you can boil something before it's actually ready to. Okay? Before it's typically ready to. And this is why whenever you're going up mountains or you're going into deep caverns, this is why the boiling point of substances actually changes, the boiling and the freezing point technically. And so this point right here, the critical point, the pressure is irrelevant. You're at a point where this substance is always going to be gas. And of course, depending on the substance, your critical point is going to change. So let's look at another example. This is CO2. Notice it has the same three zones. We didn't see the supercritical region on the first chart that we saw, but it doesn't matter. It still has solid on the far left, liquid right here in the middle, and then gas. Why is the gas zone so much bigger? Well, where have you seen, aside from dry ice, you don't see CO2 is not just freezing on the side of the road. And I don't see too much liquid CO2 in the stores. It's because CO2 naturally wants to exist as a gas. Where we see water, it's pretty much even. Water is pretty okay being all three different states of matter that we're looking at, but look at how drastically different they are. Even the line is going a different direction. So all butts are unique, people. All butts are unique, and that is the phase change diagram. So what can you be asked with this sort of thing? Well, they could give you questions in charts that look very similar to this, where instead of actually labeling all the zones, they just, label A, B, C, that sort of thing, and say, as you go from A to B, what's happening? As you go from A to C, what's happening? And notice that this phase change diagram, this butt diagram, can actually showcase sublimation and deposition, because I can go straight from solid to gas, gas to solid, without hitting that liquid zone. Very, very, very important. Pressure. Super cool. As of right now, let's describe it as this. It's essentially how much you're squeezing the substance. More pressure, more squeeze. Less pressure, less squeeze. And you can let it express itself more. Which is why, if I decrease the pressure, it can express itself more. It can spread out more. It can spread its wings more. Maybe leave the nest and become a gas preemptively before it's actually meant to boil. That sort of thing. So very, very, very cool.